Okay, we're going to begin. So in today's webinar, we're going to focus on optimizing both traditional and open source databases. But before we begin, I think we should do a couple of introductions. My name is Ash Rexuler. I'm a sales engineer at SolarWinds. I won't read my experience. I've been doing this for quite some time. And joining me today is John Patokny, and I think I'll leave it up to him to sort of introduce himself before we begin. John?
Sure, yeah. I don't have as much experience as you, Ash, but I've spent the last 6 years focused on optimizing open source databases with the Database Performance Monitor team for SolarWinds. So learned a thing or two over the last few years. I'm happy to share today.
No, awesome. Look forward to it, John. And I think before we begin, I think it's key to sort of set the context of what we mean by optimizing a database. Ultimately, the end goal of optimizing our databases is to be able to process queries as fast as possible in the least expensive way possible, while still satisfying the desired results as they relate to our business needs. So everything that we're going to be talking about today is going to tie directly to that end goal. Database optimization can be very complex, and as you'll see, there are many considerations and challenges based on the type of database platform types, the environment that those database platforms are running in, along with the application's design and that application's behavior. Because of this, it's easy to get caught up in the weeds. I like calling it analysis paralysis. And yes, John and I will go deep in various topics based on our experience. But when you step back, regardless of the environment or database platform, traditional, open source, on-premise, virtualized, cloud, etc., you'll find that the topics and techniques we cover can apply across the board, even though the key performance indicators may be different for each environment and database platform. And I think you'll find a lot of these bullets that you see here on this slide state the obvious. And the first one is no exception. Consider the environment the database is running in and the behavior of the application utilizing that instance. What's important here is to be able to understand the unique characteristics of that environment as it relates to database performance issues, so you can quickly isolate the problem. Most application performance issues are blamed on the database, and for that reason, it's critical to be able to eliminate or prove whether it's environmental or not. Is it the network? Maybe we have a disk contention issue. Are there other activities happening that are taking resources away from the database? Did something change in our virtual environment? Is it the application logic? Too many connections? Is it a poorly written query that's causing blocking contention? Or a combination of all of these? And I'm sure everyone on this webinar could share a story or two. What's key is to be able to quickly produce what I like to call the time to innocence report. You know, that mean time to innocence, so you can correlate then to the database, each key metric to the database performance, which will help isolate where the bottleneck is occurring so you can get the right folks involved to collaborate with and resolve the issue. At this point, I'm going to hand things over to John, who is not just going to be doing this real time, but historical as well. And I think you would agree, hang on. So I'm going to hand things over to John to go through the basic key metrics. You have different considerations with your environment that I covered, including resources. This also includes indexing, schema design, your query structure. They can be very complex. We're going to get into this. The next bullet point that I'll kind of hand over to John is to really talk about the metrics, the key metrics that tie directly to each layer within your application. So with that, I'm going to hand you over to John, where he's going to impress you with his wisdom. I had my I got my my tongue was tied there for a second.
No worries. Yeah, like you said, databases are really complicated, and there's a ton of metrics that we can look at to understand what they're doing and why they're behaving the way they are. You know as well as I do, you know, there are hundreds, if not thousands, of counters that databases that we're looking at can expose on their performance, as well as looking at what the the operating system that they're being hosted on for the server is doing. And then, of course, if you're running in a cloud environment like Amazon or Azure, then they're going to have some of their own metrics as well that they publish. So it's very easy to get lost in all the different counters that we can track. And we'll get into a little more detail on which ones to pay different attention to for different areas later. But my kind of rule of thumb is if you're only going to pay attention to one thing, pay attention to the work that the database is doing, right? Look at the queries that are running on it and how they're behaving. That's going to tell you the most important details about what's going on with the system. And it's really, at the end of the day, what we care about the most. Everything else is really in a supporting role, right? It's going to tell us whether or not the database has enough resources, if it's configured to take advantage of the resources we've given it. And so I like to use kind of the 80-20 rule when I'm looking at performance for my database. I spend about 80% of my time, maybe even more, looking at what are my queries doing? Is my schema design correct? Do I have indexes in the right place? The other 20%, I'm going to look at the CPU resources, disk I/O, memory, network, all that stuff on the server, and looking at the configuration of my system and making sure that I haven't bungled something that is going to hamstring the performance of the database. But really, the majority of the benefits come from optimizing the queries and optimizing the data model. And of course, we need to track the behavior for the system continuously to get a better understanding of, is what I'm looking at when I'm analyzing the performance of my system normal? Am I looking at an anomalous point in time? Has performance suddenly changed in a way that I need to go and track down why it's suddenly degraded? Being able to understand when there are unexpected performance changes is a big deal. And the best way to do that is just by keeping eyes on it as often as possible, all the time, ideally.
No, hey, John, I couldn't agree more. That historical trending data is absolutely priceless. And the last bullet item here is, as I mentioned, it's sort of stating the obvious, so please forgive me. So, I'm going to keep it quick, but make sure you keep up with your routine maintenance of your instances, perform regular backups, right, as required by your SLAs, and make sure database statistics are current and indexes are maintained to ensure optimal performance. And what's important, though, and I see a lot of people missing this one, so I know that I'm stating the obvious, especially with the backups, but stay current with both OS and database patches, even if it's in the cloud. Just make sure you know what's going on with different versions. I've dealt with several database performance issues over the years that were fixed by either applying a patch or an OS patch. I've also dealt with performance issues that were the result of applying a patch and we had to roll back. So staying in tune with the latest release notes and patches for your instance and the environment they're running in is something to put on your checklist.
Absolutely.
Okay. Yeah. Okay. Enough with the Captain Obvious, right? and as we mentioned earlier, John and I wanted to go a bit deeper in a couple of areas, and I'm going to move forward here. We want to go deeper, specifically with key metrics and historical trending analysis as they relate to query performance and efficiency based on our experience. The first bullet point here being query response time. So most of you probably already know, but what is query response time? It's the amount of time it takes the database to process a request and send a response back. It's the sum of actual processing time plus the time a session spends waiting on available resources. This is a great metric that will quickly help you identify what queries are using the most processing power and which ones are causing your application to wait. And I know John he has some other things to add as well before I go on to my favorite metric, wait states, but John, things to add here? I know you do.
Yeah, I mean, like I said before, right, if you're going to pay attention to one thing, pay attention to what your queries are doing. Query response time is the single most important metric to look at. And the more detail we can get about what the query workload is doing, the more intelligently we can start making decisions to optimize it. We want to know generally how fast is the database. We also want to know for different types of queries how fast is the database. So getting as granular as possible, looking at all the queries that are running into your system can unveil a lot of insights about how you can make decisions to improve performance.
No, I couldn't agree more. And I know we were talking earlier before, John, and it's even those really fast queries and you were one that brought this up, where you can have it's wickedly fast, sub-millisecond, but it's that cumulative impact that it can have on the environment. So it's that cumulative response time as well. That's important to understand.
One of my favorite optimizations to point out is when clients are using an ORM and it's constantly pinging the database. And they've got a query that's really cheap, but it's half of their query workload.
Yep. No, spot on with that. And now to a subject that is, John knows, near and dear to my heart. It's wait state. And unfortunately, not all database platforms have wait states. So I started off as an Oracle DBA, and Oracle was the pioneer of wait-based analytics back in the 90s. I'm kind of dating myself there. SQL Server was soon to follow, along with other database platforms. And the idea is to measure each step. So as a query is being processed in the database, so you have an idle session, that idle session will go active, and it's going to have a number of steps that the database can instrument. And for each step of that active session, that instrumentation can correspond to physical I/O operations, buffer manipulations, locks, and other database processes, which can really help you identify where your bottlenecks are. And by understanding what those wait instrumentations represent, it'll help you get to the root cause faster. Okay, so that's wait-based analytics. John, anything to add to waits?
Yeah, just that for open source databases like MySQL and Postgres, we do still have wait state information, but I tend to find it's far less useful than what you're going to see looking at databases like Oracle and SQL Server. And so if you're migrating from, say, Oracle to Postgres, that can be a really big realignment of what to look at in your system when you're used to relying on wait state analysis. And you come to Postgres and find out that, wait states are a fairly recent addition to Postgres, and they tend to be hard to interpret and understand. So there are other things that we can look at that will help get us a more complete picture of what's going on in the system.
No, that's great advice, John. Right, as a database, Postgres in 9.6 introduced wait baits. There was a company, EDB Enterprise DB. They did have wait events because they have the Oracle compatibility layer. So they had that instrumentation earlier than 9.6, but that's a fantastic point. And I think what I'm going to do is I'm going to hand the baton over to you because I know the next topic is one of your favorite subjects. So,
query workload analysis. Yeah.
Query workload analysis.
This is where I live. Yeah. So I've mentioned a couple of times, kind of briefly here, but this is really where you want to spend your time focusing your attention. What does your query workload look like? How are the different queries that are running against the database behaving? And are there things that we can do to improve the way they behave? And that's not specifically looking at inefficient queries. That's definitely a big component of it. But it's also thinking about how our application is interacting with the database. And very frequent cheap queries is a great example of that, right? We don't want to endlessly run cheap queries against the system if we can avoid it, because even though they're individually cheap to run, it can add up very quickly. So we want to look at things like, for every query through the system, right, how frequently does it actually run? How expensive is it to run? And we can use query response time to get that information. In some databases, we can get even more detailed about how it's behaving. A good example of this is MySQL has some great stats in the performance schema that are going to tell you about how many rows a query is examining versus how many it actually returns to the user. That can give you an idea of how efficient it is in terms of its indexes that it's using. We can look for sorting operations that are going to be really expensive for the system, identify missing indexes specifically. We want to make sure that our queries are actually using indexes in almost every case. There are small edge cases where a full table scan is fine. If you've got a small table of 10 rows, you don't need an index, right? But if that table is going to grow, you better make sure that there's an index in place.
Yeah, I always say if you can write your entire table into memory, it's okay. Full table scan's okay in most cases.
Exactly.
Yeah.
Anytime you have a data set where it can grow over time, it's better to be proactive and index a table and make sure a query is using an index, because it's always those tables where people are like, yeah, this is going to grow, but it'll grow really slowly. And all of a sudden it's grown 10 times faster than they expect. And their system is 100% CPU utilization because that query has become insanely expensive.
Yeah, and then the optimizer is all whacked out too, just because of the data and the stats. Yeah, no.
This is another reason why continuous monitoring is important too. But so I'm digressing a little bit, but when you're looking at the query workload, we want to identify a couple of patterns here. Which queries are really hitting the system most frequently? Which ones are most expensive? And when we're looking at those expensive queries, we can do things like capture execution plans. We want to do this not just as a one-off, but again, also kind of a periodic practice, because if you have a query that's inconsistently choosing an execution plan, that can give you variable performance. So keep an eye on that and look for those expensive operations in the query. I think for both MySQL and Postgres, we've got cost-based optimization information in the explain output. So I usually draw my eyes right to what is the largest cost phase of the execution plan. And I pay special attention to those full table scans. So for MySQL, type equals all. For Postgres, look for sequential scan. And then also sorting operations, because that's another area that scales pretty poorly as you start increasing the number of rows that's being processed. Again, though, more broadly, think about how your applications are interacting with the database. And this is a really important point for making sure that performance analysis and optimization is kind of a team effort, because if you're an outsider and you don't really understand what an application is doing, the best that you can do is take the queries it's issuing and optimize them with appropriate indexes. But in a lot of cases, you can find out that there are ways that we can get around even querying the database at all. Or maybe there's a much cheaper way that we can query the database that will still satisfy the application's needs. Back before DPM was part of SolarWinds, we were Vivid Cortex, and our founder, Baron Schwartz, always liked to say, the fastest query is a query that you never run. And that's something I really kind of took to heart, even if I didn't want to sometimes.
No, you're spot on, John, with that. I couldn't agree more. I think it's really understanding it is a team effort, and it's understanding the business requirements. I can't tell you, I have several war stories where they were putting additional load, and then I talk with the team. It's like, oh, we don't need that anymore. We needed that last month, but not anymore. Performance problems went away. Yeah. Story after story. So that is awesome information. And just to add to what John was saying, just everything you mentioned was fantastic. But when I think, and John alluded to this, when I think of query workload, I think in terms of inefficient query workload. So I'm fine with queries that are consuming resources if they're doing exactly what they were written to do in the most efficient way possible, to satisfy those business needs. But what I want to know is which queries, and John was talking about this, which queries are reading too much data, and by doing so, eating up more resources than needed, and more than likely causing other queries to wait. So, John mentioned checking for aggregation, your averages, your sums, anything that's sorting, or order by operations are very useful. But what I like to evaluate, and I kind of call it the CRE, or the cache read efficiency, which is the ratio between rows returned or rows processed to logical reads for SQL Server, buffer gets for Oracle. I use a general rule: if the ratio is greater than 1 to 5, I'm going to assume that there's room for improvement. And what do I analyze? I start analyzing the plan or plans to identify the inefficient steps within that plan. So it's also important, if possible, to capture the plans as queries are executing. You can run explain plans, but in some cases, as John mentioned, the data can change. So a plan that was used at midnight or at 8 a.m. may not be the same plan at 8 p.m. or 5 p.m. So I think that's important. When I'm looking at a plan, what I do is I'll go through the plan. If it's SQL Server, I'll look for operation steps that are named logical ops. You can write down that logical ops. So if you're parsing through the XML, you look for logical ops. And then you're also looking for a word table or clustered index or index. In essence, I'm looking for where the data is coming from. And then for Oracle, I'll look at operation steps that contain index or table access. And then from there, you'll want to look at the number of rows, compare that with the actual rows in the table, and if possible, pull out the predicate, which is the portion of the where clause associated with the excessive reads. Is that indexed, so on and so forth? Where's the data coming from? That's ultimately what we're trying to figure out. And then from there, you can look at the table to see if existing indexes are being utilized. Are they current? Are they being used? If you need to add an additional index, change one, or maybe you just have to rewrite the query. You may also want to take a look at the tables just for best practices. Are there primary keys, foreign keys? Are the foreign keys indexed? So on and so forth. John, again, I didn't mean to interrupt there, but wanted to interject. Feel free to add more before we go on to, I know, another favorite topic of yours.
No, I think you closed that one out nicely.
All right. All right. Well, let's move on to system and internal resources.
Yeah.
Which once again I'm going to hand over to you, John.
So the biggest thing to know about system and internal resources, this blends together a lot. So we're going to talk about it together. Again, think about the 80-20 rule here. Focus on your queries, but then everything that we're talking about here is going to be kind of supporting role information for the database workload. Do we have enough resources to process the work we're asking the database to do? Both at the operating system level, those fundamental metrics like CPU utilization, how much memory is being used by the system, is the disk able to keep up with workload, how much network bandwidth are we consuming? And then also there's metrics within the database that's going to help us understand if it's starting to run into problems. Things like, what's the cache hit ratio for the database's internal cache? This is a big thing for both MySQL and Postgres, and probably for just by any database here. If we're serving data with disk reads, then query performance is going to get a lot slower, even if you're using solid state drive. Also things like internal queues within the system. These, again, are complicated systems. There's queues everywhere inside the database that is processing work. So we need to make sure we're not dealing with some internal resource that's gotten full. And also background processes. I always like to think about like vacuum for Postgres, right? We need to make sure that the vacuum process is running effectively, or that the background checkpointing process is keeping up with the workload. That's going to have a big impact on performance. But generally speaking, you can go through and look here and just make sure that we have enough capacity. I like to look and see, is there enough CPU headroom? Once we start getting beyond 50%, we might want to think about adding more resources. Another neat trick that you can use here is looking at the number of concurrent queries for the database workload, things like threads running in MySQL or number of active backends in Postgres, and compare that to how many CPU cores you have. If concurrency is higher than CPU cores, you might benefit from more CPU. For memory, just make sure that you're using memory effectively. MySQL and Postgres are different in this respect. MySQL wants to use all the memory directly, so you give a lot of cache to the database. Postgres actually relies on the operating system a lot. So if you see memory in use, near the top limit, then that's actually a sign that things are configured incorrectly. And then when we look at disk I/O and network bandwidth, how much I/O is happening on the system. If we're seeing a lot of reads, it's usually a good sign that you need to check the cache hit ratio for your database. That might be a sign that we're starting to see a lot of queries that are reading data outside of your internal cache, and we need to increase memory so the database can fit its working set in memory. And network bandwidth, paying attention to how much data is going over the wire. I spend a lot of my time looking at Linux systems, so the netstat info here is really helpful for understanding if we're running into bottlenecks. Looking at things like packet retransmissions, if we're seeing dropped packets, timeouts, that'll give you a lot of information on whether or not we're seeing network bottlenecks. Although one thing to keep in mind there is that clients can have retransmissions costs too. So we need to look at things downstream too when we're looking at the network.
Yeah, no, that's fantastic stuff. And along the same lines, Oracle, SQL Server, all the different database platforms are going to have different metrics. So I think it's important to understand each one. Now, for me, and John knows this, I pull and I wave my weight-based analytics flag when it comes to metrics. Maybe it's my age. I can't remember all the different metrics that they throw at us every single release, it seems, every different platform. But for example, so again, to just reiterate, what I'll do is I will, instead of depending on specific metrics, I personally will rely on the weights to help identify where the contention is with that particular instance, since each weight instrumentation will be directly tied with, for example, the buffer pool, latches, I/O latency, or queuing. So for example, if I see a lot of CX packet, which is caused by parallelism, I may want to correlate that workload, that query workload, with signal weights to see how many sessions are waiting in the queue. Normally, you want this to be below 25%. I also want to emphasize how important it is to understand the limitations of any environment or database platform. For example, some versions of SQL Server will have limitations, regardless of how much horsepower you throw at it. I've dealt with this over the years, and it was frustrating. I couldn't peek past that 50% CPU utilization. I want to see 90%. I want to see it pegged. For example, SQL Server Standard Edition has a max compute capacity of 4 sockets or 24 cores, which reminds me of a quick story, so bear with me. I think it's good. And I must confess, this didn't happen to me personally, but when I heard it, it really resonated. Basically, there was a SQL Server Standard Edition. DBA was setting everything up, and they wanted 12 CPUs. Virtual admin configured 12 CPUs, and all of a sudden they looked at everything, and they went to the task manager, and they saw only 4 of the 12 were being used. Well, when they stepped back and they worked together, collaborated together, the virtual admin was able to spin up 4 CPUs, the limit, and add 3 cores each. So they were able to maximize that horsepower. So that's key to really understanding the environment, limitations, whether it's at the kernel, whether it's database configuration in different versions, you might be limited. Okay.
I love that trick with the CPU virtualization.
Yeah. So, hey, John, do you have anything else to add before we move on to the next cloud bullet?
Your story does remind me that, a lot of the configuration that we like to do with databases to make sure they're using resources, when you're looking at a smaller database, the configuration probably matters a little bit less. It's once we start scaling up and getting to larger instances, think many cores or dozens or hundreds of gigabytes of RAM, where we really start to need to pay more attention to the operating system configuration and the database configuration. Well, of course. I actually have some stories of my own of Linux configurations that cause 1-minute lockups for customer databases. In particular, if you're running on Linux and you're using transparent huge pages, the larger your database server gets, the more likely that memory compaction will stall the system. And I've seen that happen in a couple of different cases with clients where they have huge MySQL databases that would have very high variation of query latency, that was tied directly to memory compaction, or even in one case that I'm thinking of, the server would actually pause for 30 seconds to a minute while compaction ran so it could allocate memory.
Mm-hmm.
These are the kinds of problems that we don't see at smaller scale, though, right? If you go and look at a server with 15 gigs of RAM and you have transparent huge pages turned on, it's not as big of a deal because memory compaction is faster at that scale.
No, spot on. Yeah, and I've dealt with similar ones, especially with Linux. It was semaphores and message queues where we had to change the kernel. Yeah, and I know you kind of you have more information regarding the cloud. I know you're kind of an expert in the CloudWatch and AWS. And, so the only thing here that I want to add or mention as we kick off this bullet, as we move to the cloud, we're going to have less control over the environment. We're not going to be changing kernel parameters or anything like that. And there's going to be more of an emphasis on query performance. And, John, before you dive into your portion, I just want to talk about Azure and just particularly one metric that probably everyone here is familiar with, which is DTU. I remember, this is a few years ago, cat got my tongue there, when I heard DTU, I was like, what is DTU? Well, DTU, and again, you probably know, stands for Database Transaction Unit. And then even when someone told me that, I'm like, well, and what does that mean? Well, so basically, it's a way Microsoft came out with this DTU unit, and it provides a way to roughly measure a combination of CPU, memory, and IOPS. So think of a quadrant, the Gartner quadrant, but it's a DTU quadrant. And so one, you're going to have CPU, another quadrant, you're going to have memory, another one, you're going to have read IOPS, and another one, you're going to have write IOPS. But what blew me away, as they were using this as a way to measure the tiers, how they charge you based on different tiers and the workload. If you exceeded any one of those quadrants, whether it's memory, whether it's CPU, whether it's read IOPS or write IOPS, if you exceed any one of those, you can configure your environment to jump into the next tier. And Microsoft's happy to charge you for that next tier. But if you don't have that and you fill up one of those quadrants, you're going to see serious degradation with your database performance. So I think it's really important to keep track of those. And you can actually keep track of each specific quadrant, not just DTUs, but you can keep track of each individual one. But it's so important to understand. And I know, John, you mentioned we were talking before about the tiering, and I know understanding the cost and understanding the application and how it's utilizing this environment. And that's going to be my segue to kind of pass the baton over to you to talk about Amazon and CloudWatch and all the goodness that you know there.
Yeah, and I think that's a perfect example, by the way, Ash, that, when we move to the cloud, a lot of people want to just outsource the concern of managing their databases. I mean, who wouldn't want to not have to care about that anymore and just write their queries and focus on their schema? I certainly would. But the problem is that, with every cloud provider, it's not just Azure and DTUs. You've really got to read the fine print. You got to read the docs and understand what exactly you're going to be charged for, and also understand what you're going to get metered on. Because in every cloud provider, there is something where you're not going to expect it, but they're going to bill you by the operation or by the byte or something like that. When we're talking about Amazon, one of the things that always blows my mind is the differences in how instances can be billed. So, for example, if you spin up an Aurora instance, using Amazon's proprietary database model, they will bill you based on IOPS consumed. So disk traffic becomes more expensive. In all forms of RDS, outbound network traffic is also billable. So we have to think about how much data we're passing outside of our VPC, passing to different services. That can actually start to become a big concern from an expense perspective. Of course, anyone who's used Amazon probably understands the idea of CPU credits. So they're burst tier instances that have a credit balance, and if you run out, then your CPU usage gets throttled excessively. The same thing also applies to their disks as well. And this is one of the other ones that I originally did not know and learned about through a postmortem from a friend. EBS volumes, elastic block storage, it has a burst balance on how much IOPS you can consume. If you run out of burst credits for your disk I/O grinds to a halt. They are metering the amount of performance you can get out of the disk. And so we have to pay attention to these specific resources, these budgets that there are on our system, and how many resources we can consume. Because if your burst balance goes to zero, then your performance is going to go through the floor.
So, no, that's good. Yeah, no, spot on. So the devil's in the devil's in the details, right?
Exactly.
So no, that's great stuff. And I'm going to kind of segue here into we want to drive things home and really reemphasize the importance of historical trending analysis. Again, John loves this, so I'm going to once again allow John to kind of comment and bring us home here.
Yeah, I've probably said this 3 or 4 times already, but optimization is not a task. Performance is not something that you go and work on once in a sprint and call it done. It is a continuous practice, the discipline that your team needs to take on, and it really starts with baselining your systems and understanding what normal looks like. If you go and look at your database performance once in isolation, you don't know if that was the system at its lightest load or at its heaviest. You don't know what was going on is normal or not. And so we need to understand what's normal and have eyes on how the workload is performing, how the system is performing what its resource utilization looks like. And once we understand what normal looks like, we just need to keep monitoring with every change we make. And changes are not just changes to the database. It's not adding or removing indexes. It's also every application release for the applications that are talking to the database. It is, as Ash, you mentioned, upgrading the operating system, upgrading minor versions for the database. That can have an impact on performance. We want to make sure we understand it and we're paying attention to it. So measuring every change and knowing whether or not it made performance better or worse. I like to say to people, there is no substitute for a developer that understands how their system should work looking at performance for their systems. That is going to be the best way to spot potential optimizations and improve performance over time, is to have the people that are writing the applications, that are using the services, monitoring for any regressions or any unexpected behavior. And it's okay to have a dedicated performance team or somebody who's in charge of infrastructure and monitoring, but that doesn't mean that the rest of the team is exempt from thinking about database performance. It's something that we all need to internalize and collectively take a look at.
No, well said. I mean, I really can't. I can't add to that other than guess what can help you. Tools can be a developer, a DBA's best friend, and this is kind of my favorite portion of the webinar, and that's really to highlight two amazing products that SolarWinds offers when it comes to database performance monitoring. One is our SaaS solution geared towards open source databases. Used to be Vivid Cortex. Now it's been rebranded to be Database Performance Monitor. And then on the left, you see a product called Database Performance Analyzer, DPA, formerly Confio Ignite. What we're going to do is we're going to dive into kind of the demo portion. I'm going to hand the reins once again to John to demo DPM, and then he'll hand the reins to me to go through DPA, and then we're going to open it up. I think we're going to have a poll question, and then we're going to open up for a Q&A. All right, John, with that, I am going to make you the presenter so you can share out your screen.
All right. And try and keep me honest on the time here. I don't want to steal it all away from you.
That's okay. I can go quick.
So we'll dive into DPM really quickly here and talk about some of the things that we can do that apply directly to what we've talked about in the webinar here. So just starting off from the home page, right? We want to understand what our database workload looks like and what our resource utilization looks like. And so you can see that right from the summary here. We're looking at query throughput, how many concurrent queries are happening on average in the system, what our query latency looks like, that response time, and also, of course, any errors that are showing from the workload. So I can use this as a starting point to see, is there something that is happening that is strange in the database, right? Something that catches my eye immediately is the spikes in concurrency that are happening periodically here. Maybe there's a cron job that's doing something that is causing lock contention, or it's particularly abusive to the disk. We can dive in and take a closer look at what queries are actually causing that behavior and see if there's something we can do to make them a little bit better. Maybe we can average that out over the interval instead of having one big spike. And we also want to keep an eye on resource utilization, right? So CPU, network bandwidth, disk I/O, memory usage, those metrics we talked about for the operating system, keep an eye on that as well. Whether you're on-premise running dumb bare metal, or if you're in the cloud running on cloud services like Amazon RDS, we'll take a look and see, is resource utilization looking okay? And from here, we can dive in and get a better idea of what's going on in the workload. So if I want to get a better understanding of that concurrency spike, there's a little what to do next here that will help me dive in and figure out where to go based on what I'm seeing. So let's say I want to look at this spike in concurrency. If I follow through here, this will take me to DPM's profiler. Again, queries are really what I live and breathe. And the profiler will let me understand what queries are driving the workload for my databases. So right now you can see top 20 most time-consuming queries in my workload. What jumps out to me is I've got a couple of insert statements here that have some spikes that matches up with the spiky pattern and concurrency that we saw. So these inserts are probably the culprit for my pattern on the summary page, right? A lot of inserts coming simultaneously that could be causing spikes in disk I/O, could be causing spikes in concurrency in the system if they're competing for a lock on the same table or same index. So that probably explains the behavior I'm seeing there. We might need to adjust the application to make it easier to understand what's happening. And we can slice and dice by a lot of different metrics too. It's not just time-consuming queries. We want to understand everything about the workload. So if I filter on different things, I can look for queries that are running frequently against the database or examining lots of rows, even missing indexes. We want to find queries that are doing full table scans. We can find that too. And we can change our ranking, find areas where there are full table scans. It looks like this is actually new behavior here. So I can jump into the query and take a look to see what's going on. That's going to let me look at different samples. Each of these dots that you see is a sample execution. And if I click on a sample, it'll let me see the explain plan. With a tabular format for people who aren't used to reading MySQL explain output, as well as the raw JSON that comes from the database. So this will tell me, in this case, I'm doing a full table scan over 500,000 rows. That's quite a lot more than 10 or 100, so it's probably something I want to look at, adding an index to my system or changing the query to take advantage of an existing index. There's a lot of ways to break down your workload in DPM. We do not have time to go through all of them, but one thing I do want to touch on is we can help you understand what is normal in the workload. So when I'm looking at behavior in the profiler, I have the ability to quickly compare it to historical data and see if what I'm looking at is the usual behavior or if it's something new that's happened in the system. So if I want to look and see what my query workload looked like yesterday in comparison to the last hour that I'm currently looking at, we can pull that up and see on top here for each query, we've got the most recent hour of data. Underneath is 24 hours in the past. And you'll notice there's a little column here on the right that shows me the relative change before versus after. So every time we make a change, we can very quickly come into DPM and understand the impact on performance for our systems and sort to find the queries that have the largest increase, largest decrease in change. Find out if our systems are getting slower overall or getting faster. I know we're running out of time quickly, so I will end things pretty shortly here, but one last bit to talk about is there is information on what the database is doing internally in addition to the query workload within DPM. We've got a number of pre-built dashboards that you can take a look at. It's going to show you information on resources for MySQL, Postgres, MongoDB, all those supported databases that DPM can monitor, as well as the resources for the server, CPU, disk I/O, memory. And we do have some built-in resources to help you analyze the performance and efficiency of those metrics. So for example, on our notebooks page here, there's a built-in template that I can use to inspect my MySQL database, my MongoDB database, my Postgres database, and see if everything looks healthy, looking for any bottlenecks internally in the system, as well as evaluating the query workload. So out-of-the-box resources to help you do this kind of evaluation on an ongoing basis, as well as tools that are really query-centric to help you and the team evaluate how things are changing over time as you're changing your applications. That's probably a good point for me to leave off on. So I will turn things back over to Ash, and you can give people a quick demonstration of DPA.
No, I wanted you to keep going, John. That was great stuff. All right, I'll
we
take.
Are running out of time, and I want to keep. I know you've got some stuff too.
Yeah, I'll take the reins here, and let me share out my screen. So just for the sake of time. So again, this is all tied to optimizing a database and that trending data. Each of these tools collects information like down to the second, and then it gives you that historical trending data that's just crucial and valuable in helping you understand what's normal, so you can be proactive and look for things that are not normal that John was talking about. So this is DPA's main dashboard. I'm not going to spend too much time here. Fairly self-explanatory. The chart on the left, I have to point out, DPA is what I like to refer to as a response time analysis product. And then it embraces something called weight-based analytics that I talked about through the session. But the chart here is going to give you kind of a 2-week snapshot of your top 5 busiest instances from a cumulative wait time perspective. So you can see if you had a spike in cumulative wait time, maybe 6 days, and things can run in parallel. You can have hundreds of concurrent users all using the same application logic. So just because this is greater than 24 hours, what's important to understand and know is what can that particular instance handle. We're going to track trending patterns as well, whether your instances are trending up or trending down. Below these charts are alarms that are going to give you the health of the instances that are being monitored. And just for the sake of time, I'm going to focus on the wait time alarm and the tuning alarm. But before I dive into that, I also want to point out that DPA does support monitoring multiple database platforms that you see here. I'm going to be focusing on SQL Server. The wait time alarm, what it's going to do is it's actually going to use a machine learning algorithm that's going to look at the last 90 days of trending data for each hour. And then it uses seasonality, knowing that workload is different. You have backups that run at night, SQL agent jobs that are running. You have your core business hours, maybe from 8 to 5, or you might have banker's hours. Your workload during the weekend may be different than during the week. So this algorithm takes that into account. And I'm going to dive into this one particular instance. So we talked about pattern analysis and understanding kind of what your workload looks like. DPA, after it's collected and it's monitoring and collecting user active sessions every second, less than 1% load, it's going to present this information. It's multidimensional. It's going to default to the SQL dimension. So when you click on an instance, it's going to show you the top 15 queries based on cumulative wait time. So the vertical bars are a wait time summary for each day. And I can hover over the slice. The bigger the slice, the bigger the wait time. And you can drill in down to the second. I can look at my slowest queries. I can look at a typical day, so it's taking those 30 data points, merging them all together in a typical day. But what I want to do is draw your attention to the anomaly detection. So instead of having to look back into a pattern analysis for each day, weekend, and the differences, the anomaly detection algorithm is going to do that for you. So the whole idea is we are going to point out an anomalous day, so very quickly you can drill in to an anomalous day. And if you'll notice, we have a big bar, and we used to promote follow the big bar methodology, and it's still applicable for most of the time. But a lot of times you have big bars, at 2 a.m., 4 a.m., which are normal, and that's what the machine learning algorithm is going to identify. In this case, this is a normal workload, and in fact, it's 16 minutes more performant than usual. Our anomalies occurred at 11 a.m. and at 4 p.m. So very quickly, we can drill into an anomalous hour. Now DPA is showing us the queries that are impacting the end user experience. We know the impact. In this case, it's 8 minutes and 31 seconds. But the most important question that DPA is answering is with the where. Where is this query spending its time? And this is where we get into weight-based analytics. So the weight instrumentation. So in this case, it's spending 65% of its time consuming CPU, consuming resources, which is good if it's doing it efficiently. So in this case, SQL Server specifically, an active session can be one of 3 states. It's either running, it's runnable, or suspended. So this represents the running runnable time, but we have a suspended instrumentation in a locked category. So this particular query is the victim. It's being blocked, and then very quickly I can go into the blocking chain. I want to get to root cause. DPA will show the lead blocker, including any idle blockers. So we have this nice feature that will actually go back in time, take you to the portion of that connection prior to that object being blocked. A lot of times people blame a query. It's not necessarily a query that causes blocking or contention, but it's actually the application logic that can cause the blocking. And this is one of the hardest blocking scenarios to resolve. So DPA very quickly would bring us to the connection where the blocking occurred. Now we can dive in to that particular query in question. We can take a look at the supporting data, who ran it, what application did it come from, look at the SQL text. DPA will give you a full-fledged analysis for every single query that it's monitoring based on past performance. And we can correlate statistics. So for example, if I want to go back in time, again, speaking of that trending, see, has this always happened? Has it always been a problem? I always like to see what are the drivers of the response time. So here, very easily, you can see historically we've had a systemic blocking problem with this portion of the code. It was worse later on. It's improved, but really it's just because of our workload went way down. And you can correlate resource metrics as well. So just a great product for getting that insight and pattern analysis of what's going on. What I also love about DPA is that it will analyze your plans. So if you go back to the home, every night after we collect all of our information, we're going to analyze your queries. What I spoke about earlier, that CRE, the cache read efficiency, DPA will do the exact same thing for you for Oracle and SQL Server. So I filtered by tuning, and then if I go into the tuning tab, you can see our analysis of the queries on the left-hand side, and then on the right, we're going to show you our analysis of the plans, and we went through, looked at the inefficient steps, looked at all the data, aggregated that, and then we're presenting it at the table level. Why? Because that's where data comes from. That's where indexes are. So very quickly, this is sort of your heat map. DPA brought you to X marks the spot. You still have to dig to get the treasure, but you can click on that mark, the heat map of your schema. On the left-hand side, you're going to see a list of the queries that are driving the inefficiency. And then if I click on a hash on the right-hand side, we do some math for you to show you how inefficient it is. We will show you the actual plan that we analyzed. And even for a seasoned DBA to sort of go through, look at all the stats, we will pull in the missing index advice from Microsoft. Some SQL Server DBAs like this feature, some hate it, some are indifferent. The reason is you need to know more about the table in question, and that's the gap that we fill. So not only are we going to show you the DDL and the index recommendation, but we're also going to show you other queries that have the identical index recommendation, so a more holistic view as well, plus our analysis. So we'll break it down. We'll show you the inefficient steps. We'll compare that to the actual rows in the table, the churn, how often is the data changing, when was the last time stats updated, do we have any fragmentation. We'll compare the predicate to existing indexes and tell you whether or not you do have an index. So this is based on actual workload. And we'll even go and look at your table and determine best practices, whether or not your foreign keys, as I mentioned earlier, are indexed or not. So great information, a great feature. With that, I can spend hours and hours on this, but what I'm going to do is I'm going to stop sharing, kind of end my demo here just from a time perspective, kind of get into kind of the Q&A. You mean we were that thorough, John? That's awesome.
Well, everyone is falling asleep. We'll never know.
That's right. But you know what? Boom. We spot on 2 o'clock. All right. Thanks, everyone, just for the session. Hopefully you found the information that we shared beneficial in optimizing your databases.
Yeah. Thanks, everyone.